The first theoretical cycle presented is called the Otto cycle, and in French it's called cycle de Baudot-Rochat, but it corresponds exactly to the same cycle. This kind of theoretical cycle is only used in order to describe what's taking place in spark ignition engines. So, once again, we'll use an indicator diagram with pressure for the y-axis, volume for the x-axis, and the atmospheric pressure, the minimum volume at the top dead center, clearance volume, and maximum volume at the bottom dead center. So, where do we start? Now we have a two-stroke cycle, or at least the four-stroke engine is described with the two-stroke theoretical cycle. We don't have the admission anymore, so we'll start with the first point that we will write as point 1 at the end of the admission. So at the bottom dead center, maximum volume and admission temperature corresponding to the atmospheric temperature. That would be point 1. For the Otto cycle, the first transformation is the compression stroke. The compression is considered as adiabatic and reversible, and in an ideal gas with constant thermophysical properties. From a thermodynamic point of view, we can write that the product of pressure times the volume at the power gamma, the Laplace coefficient, is equal to a constant. So, if we want to plot this transformation in a PV diagram, it will look like a hyperbole, and the pressure will increase this way up to what we call point 2 once at the clearance volume, so at the top dead center. So this is the compression. Second stage or second transformation is the combustion. For the Otto cycle, we do one big approximation. This is used in order to describe the spark ignition engine, and it was described before that this combustion is very fast because the fluid is already premixed between the fuel and the combustive. So once the combustion is ignited somewhere at the spark plug, then the combustion spreads everywhere very fast, and the approximation that is done in the Otto cycle is that the combustion is instantaneous. If it's instantaneous, it means that the piston has no time to move, and if the piston does not move, then the volume remains constant. So from a thermodynamic point of view, it's what we call an isochoric transformation, isochoric with a constant volume, and it's an isochoric heat input, so the fluid will receive heat that will increase both the pressure and the temperature. So isochoric constant volume, it remains at the top dead center until a higher pressure at what we will call point 3 for the end of the second transformation, which is the combustion. Then, third transformation, once the combustion is over, we have the expansion. Once again, we do the same approximation as for the compression. We consider that the expansion is adiabatic and reversible, so P times V at the power gamma, Laplace coefficient, is once again equal to a constant, so we find an hyperbolic shape like this, with the same coefficient than for the compression, up to a new point called point 4, and this is the expansion. And finally, we have the most, I would say, bizarre transformation. It's the imaginary transformation that is used in order to replace the admission and the exhaust. And here we want to bring back the fluid to the initial state, so to connect 4 to 1. And if we do that, we have an isochoric transformation because the volume remains constant, and we need to do a cooling in order to decrease the temperature and the pressure. So that's an isochoric cooling that is representing the exhaust and the admission, and also the fact that the exhaust temperature is much higher than the inlet temperature. So this is for the Otto cycle, which is the most basic cycle in order to describe the thermodynamic transformation inside the spark ignition 4-stroke engine.